Mechanics, Part 1. Mechanics, taken as the name for just one of the physical sciences, would merit no place on a small list of basic focal terms, but the word mechanics means more than that. In the tradition of Western thought, it signifies a whole philosophy of nature, and it connotes a set of fundamental principles under which it has been thought all the physical science can be unified. The principles of mechanics have been applied not only in statics and dynamics, which are concerned with the action and reaction of bodies at rest or in motion, but also in acoustics and optics and the sciences of heat, magnetism, and electricity. They have been extended to astronomical phenomena to constitute what is called celestial mechanics. They have been thought to govern the action or motion of invisible particles or waves, as well as the familiar bodies of ordinary experience. In the range and variety of the phenomena it covers, mechanics would seem to be coextensive with physics. Such, at least, appears to be its scope at one stage in the development of natural science. We shall presently consider the dissatisfaction with the mechanical point of view, which causes scientists in our own day to hail the replacement of classical mechanics by the new physics as a great advance in science. The intellectual significance of this change can be compared with that earlier revolution in the 17th century, when the new natural science founded on the achievements of Galileo, Huygens, and Newton replaced the physics of Aristotle, which had long reigned as the traditional philosophy of nature. What Einstein calls the rise and decline of the mechanical point of view thus seems to provide an apt title for the story of three stages in the history of science, in only one of which does the whole of physics appear to be dominated by mechanics. One way, then, of understanding the importance of mechanics is in terms of that story. Other chapters, such as astronomy, change, element, matter, physics, space, and time, and perhaps also cause and hypothesis, tell parts of that story, especially the part which turns on the differences between Aristotle's physics, which is neither experimental nor mathematical, and modern physics, which is both. This chapter focuses on issues which fall largely within modern physics, issues belonging to that part of the story which, in the great books, begins with Galileo, Huygens, and Newton, and runs to Fourier and Faraday. The story itself does not end there, but the point to which Faraday carries it suggests the sequel in Clerk, Maxwell, and Einstein. Just as Galileo's point of departure, reflects antecedents in Aristotle. The great books state the issues sufficiently well, though they do not tell the whole story. That can be fully documented only by a host of supplementary scientific classics in various fields, such as the works listed in the additional readings. In modern times, it is accepted that physics should be both experimental and mathematical. No one questions the ideal of unifying the physical sciences and finding the unity in nature's law. But the question is whether that unification can be achieved under the aegis of mechanics. And the issue is whether physics should gather its experimental findings together under purely mathematical formulations, or should also try to give those mathematical formulae a mechanical interpretation. The issue involves more than a question of scientific method. It concerns the ultimate aim of natural science and the kind of concepts it should employ to fulfill this aim. Should the scientist seek to do no more than describe the phenomena of nature in terms of the simplest and most universal mathematical relations? Or should he go beyond description to an explanation of the phenomena in terms of their causes? When the issue is thus stated as a choice between being content with description or striving for explanation, it appears to be broader than the question whether physics should or should not be mechanical. Even granted that explanation is desirable, does it necessarily follow that physical explanation must employ the principles and concepts of mechanics? Aristotle's physics, it can be argued, provides a negative answer. His various physical treatises represent a natural science which tries to explain the phenomena without doing so mechanically, just as it tries to describe the phenomena without doing so mathematically. That the connection of these two features of Aristotle's physics is not accidental seems to be indicated by the conjunction of their opposites in modern physics. When in the 17th century the physicist describes natural phenomena in mathematical terms, he explains them, if he tries to explain them at all, in mechanical terms. The laws of mechanics, writes Descartes, are the laws of nature. Huygens opens his treatise on light by referring to optics as the kind of science in which geometry is applied to matter. But he at once expresses the desire to advance this branch of mathematical physics by investigating the origin and the causes of the truths already known in order to provide better and more satisfactory explanations. Such explanations, he thinks, will be found only if we conceive the causes of all natural effects in terms of mechanical motions. He declares, in his opinion, that we must necessarily do this, or else renounce all the hopes of ever comprehending anything in physics. Galileo and Newton, as will be noted, do not unqualifiedly share Huygens' view that it is proper for the mathematical physicist to inquire about causes, but they would agree that if any explanation is to be given for laws of nature expressed in mathematical form, one or another type of mechanical hypothesis would be required to state the causes. Postponing for the moment the consideration of whether the investigation of causes belongs to mathematical physics, let us examine what is involved in giving a mechanical explanation of anything and why this type of explanation tends to occur in the causal interpretation of mathematically formulated laws of nature. Two points seem to constitute the essence of mechanical theory. Both are fundamental notions, and both are philosophical in the sense that they do not seem to result from the findings of experimental research. The first point is an exclusive emphasis upon efficient causes, which means the exclusion of other types of causes, especially final and formal causes, from mechanical explanation. As the chapter on causes indicates, efficient causality consists in one thing acting on another, but not every sort of action by which one thing affects another is mechanical. According to the doctrine, an efficient cause is mechanical only if it consists in a moving body acting on another by impact, or if it consists in a force exerted by one body to cause motion in another, or to change its quantity or direction. The notion of a force which does not work through the impact of one moving thing upon another raises the problem of action at a distance, to which we shall return subsequently. The second fundamental point is an exclusive emphasis upon quantities. Mechanical explanation makes no references to qualities or other attributes of things. Paradoxically, this point is sometimes expressed in terms of distinction between primary and secondary qualities. But as the chapters on quantity and quality point out, the primary qualities are all quantities. According to Locke, they are solidity, extension, figure, motion, or rest, and number. According to Newton, the universal qualities of all bodies whatsoever are extension, hardness, impenetrability, mobility, and inertia. Others, like Galileo and Descartes, give still different enumerations, but the point remains that the only attributes of bodies which have mechanical significance are measurable quantities. Such secondary qualities, for example, as colors and tones, belong to the physical world, as it is mechanically conceived, only by reduction to the local motion of particles or waves having certain velocities, lengths, or other quantitative attributes. We need not be concerned here with what sort of reality is assigned to secondary qualities, or how their presence in experience is accounted for. These problems are discussed in other chapters, such as quality and sense. However they are solved, the philosophy of mechanism excludes from the physical world whatever does not consist in, or cannot be reduced to, quantities of matter, or mass, motion, or force, and such related quantities as those of time and space, or distance. The 2 points of mechanical theory are obviously connected, for the kind of cause which mechanical explanation employs, to the exclusion of all others, consists in a quantity of motion or of force. Just as obviously, mechanical explanation, dealing only in quantities and in causes which are quantitatively measurable, is precisely the type of explanation which would seem to be appropriate if one felt called upon to give an interpretation of the mathematical relationships which the mathematical physicist formulates as laws of nature. These mathematical laws are, after all, statements of the relations among physical quantities which have been subjected to experimental determination, or measurement. As a physical theory, the mechanical view of nature antedates modern physical science. The atomistic conception of the world, which Lucretius expounds, contains both of the fundamental points of mechanism: the doctrine of primary and secondary qualities, and the doctrine that all effects in nature are produced by efficient moving causes. The controversy over mechanism is also ancient. Aristotle denies both points of doctrine in his criticism of the Greek atomists, Democritus and Leucippus. And in the exposition of his own physical theories, he states an opposite view. To qualities and qualitative change he assigns physical reality. He explains change in terms of 4 types of causes, not 1. He does not exclude the mechanical type of cause in his explanation of local motion. On the contrary, with respect to local motion, his theory that a body in motion must be directly acted upon by a moving cause throughout the period of its motion seems to be more mechanical than the modern theory that no cause need be assigned for the continuing uniform motion of a body along a straight line, but only for a change in its direction or velocity. What is new in modern times is not the philosophical doctrine of mechanism, but the introduction of mechanical explanation into experimental and mathematical physics, and the controversy about whether it belongs there or can be defended as useful. The so-called rise and decline of the mechanical view in modern physics is connected with experimental discoveries and mathematical formulations. It is not an alternation between success and failure on the level of philosophical argument concerning the ultimate truth of mechanical conception. When these concepts are rejected, it is not for the sake of returning to opposite notions in physical theory, such as those of Aristotle, but rather because, as Einstein says, science did not succeed in carrying out the mechanical program convincingly. And today, no physicist believes in the possibility of its fulfillment. There is a touch of prophecy in the conversation Swift imagines taking place between Aristotle and the physicist of the 17th century. According to Swift, when Aristotle was confronted with Descartes and Gassendi, he freely acknowledged his own mistakes in natural philosophy, because he proceeded in many things upon conjecture, as all men must do. And he found that Gassendi, who had made the doctrine of Epicurus as palatable as he could, and the vortices of Descartes were equally exploded. He predicted the same fate to attraction, where of the present learned are such zealous asserters. He said that new systems of nature were but new fashions, which would vary in every age, and even those who pretend to demonstrate them from mathematical principles would flourish but a short period of time and be out of vogue when that was determined. Both Galileo and Descartes restate the philosophical doctrine which first appears in ancient atomism, but both restate it in a way that suggests its utility for an experimental investigation of nature. It is significant that Galileo's statement occurs in the context of his concern with the nature and causes of heat. He wishes to explain, he writes in To Saggiatore, why he thinks that motion is the cause of heat. To do this, he finds it necessary to question a prevalent notion, which is very remote from the truth. The belief that there is a true accident, affection, or quality really inherent in the substance by which we feel ourselves heated. He denies the physical reality of heat as an inherent quality of bodies on the same ground that he denies the physical reality of other qualities. I do not believe, he declares, that there exists anything in external bodies for exciting tastes, smells, and sounds, but size, shape, quantity, and motion, swift or slow. And if ears, tongues, and noses were removed, I am of the opinion that shape, quantity, and motion would remain, but there would be an end of smells, tastes, and sounds, which, apart from a living creature, I regard as mere words. Descartes' statement of the doctrine is bolder, perhaps, in its suggestion of a mechanical program for physical research. Colors, odors, savors, and the rest of such things, he writes, are merely sensations existing in my thought. They differ from the real properties of bodies just as much as pain differs from the shape and motion of the instrument which inflicts it. The true physical properties, such as gravity, hardness, the power of heating, of attracting and purging, consist, in Descartes' opinion, solely in motion or its absence, and in the configuration and situation of bodily parts. As a philosophical doctrine, the mechanical view is not necessarily tied to atomism. Descartes opposes atomism as plainly as does Aristotle. Furthermore, Newton, who is an atomist, disagrees with both Descartes and the Greek atomists on one fundamental point in mechanical theory. The ancient atomists make the actual motion of one particle in collision with another the indispensable cause of a change of motion in the latter. Descartes likewise requires one motion to be the cause of another, and explains gravity in terms of actual bodily motions. Newton rejects Descartes' mechanical hypothesis of material vortices as the cause of gravitation. He seems to have this in mind, and to put Descartes in the same class with Aristotle, when he says that hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. The force of gravity, according to Newton, is a power of attraction which one body exercises on another without the first being in motion or coming into contact with the second. Newton acknowledges the problem of action at a distance, which his theory raises. For the most part, he lets it stand as a problem which does not affect the mathematical results of his work. But in the queries he attaches to his optics, he suggests, by way of solution, the hypothesis of an ether as the continuous medium through which gravitational force is exerted. In the opinion of later physicists, Newton's hypothesis is no less mechanical than Descartes', nor does there seem to be any philosophical grounds for preferring one hypothesis to the other. But Newton's quarrel with Descartes is not on a philosophical issue. It turns on which mechanical conception, if any at all, is to be offered. Fits best with the mathematical laws of terrestrial and celestial motion, which Newton had succeeded in formulating as universal laws of nature. Those mathematical laws, moreover, had the merit of fitting the observed phenomena, and so of realizing the scientific ideal of accurate description stated in the most generalized form. Newton's triumph over Descartes, then, is a triumph in mathematical and experimental physics, not a triumph in philosophy. Pope's couplet. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Records the triumph and celebrates the illumination of nature by the mechanical as well as the mathematical principles of Newton's physics. Newton's picture of the world dominates the mind of a century and controls its science. Locke speaks of the incomparable Mr. Newton and of his never enough to be admired book. Hume refers to him as the philosopher who, from the happiest reasoning, determined the laws and forces by which the revolutions of the planets are governed and directed. And even Berkeley, who challenges his theories of space, time, and attraction, regrets that he must take issue with the authority of so great a man whom all the world admires, as the author of a treatise on mechanics, demonstrated and applied to nature. Newton's achievement is to have accomplished an extraordinary synthesis of all that was good in previous scientific work, and a sweeping criticism of all that was considered stultifying. That so many and such varied phenomena should be organized mathematically by a theory as simple as Newton's is altogether impressive. Equally astonishing is the predictive power of Newton's laws, and the explanatory power of his mechanics, not to mention the technological fruits of the latter in mechanical engineering and the invention of machinery of all sorts. Whatever difficulties are implicit in the Newtonian mechanics, subsequently to become, with new discoveries, more and more perplexing, the scope and grandeur of Newton's book gives mechanics a commanding position with respect to the future of science for at least 2 centuries. In the century between the publication of Newton's mathematical principles and the publication in 1787 of Lagrange's Mécanique Analytique, the notion of the mechanical explanation of all the processes of nature, writes Whitehead, finally hardened into a dogma of science. In the next century, the mechanical dogma spreads from physics and chemistry throughout the whole domain of natural science into biology and psychology, and even beyond that into economics and sociology. Books bearing such titles as The Mechanistic Conception of Life, The Mechanism of Human Behavior, Social Statics, social dynamics. At the end of the 19th century, James notes the conquests which are being made on all sides by the mechanical idea. Once the possibility of some kind of mechanical interpretation is established, he writes, mechanical science, in her present mood, will not hesitate to set her brand of ownership upon the matter. James himself testifies to the persuasiveness and success of the mechanical dogma, though not without some resentment. The modern mechanico-physical philosophy, of which we are so proud, he says, because it includes the nebular cosmology, the conservation of energy, the kinetic theory of heat and gases, etc., etc., begins by saying that the only facts are collocations and motions of primordial solids, and the only laws the changes in motion, which changes in collocation bring. The ideal which the philosophy strives for, he continues, is a mathematical world formula by which, if all the collocations and motions at a given moment were known, it would be possible to reckon those of any wished-for future moment by simply considering the necessary geometrical, arithmetical, and logical implications. Laplace had, in fact, pictured a lightning calculator who, given the total configuration of the world at one instant, would be able to bring the whole future present to his eyes. And James quotes Helmholtz to the effect that the whole problem of physical science is to refer natural phenomena back to unchangeable, attractive, and repulsive forces whose intensity depends wholly upon distance. The solubility of this problem is the condition of the complete comprehensibility of nature. In commenting on this, James admits that the world grows more orderly and rational to the mind, which passes from one feature of it to another by deductive necessity, as soon as it conceives it as made up of so few and so simple phenomena as bodies with no properties but number and movement to and fro. But he also insists that it is a world with a very minimum of rational stuff. The sentimental facts and relations, he complains, are butchered at a blow, but the rationality yielded is so superbly complete in form that to many minds this atones for the loss, and reconciles the thinker to the notion of a purposeless universe in which all the things and qualities men love are but illusions of our fancy, attached to accidental clouds of dust, which will be dissipated by the eternal cosmic weather as careless as they were formed. With the 20th century, a change occurs. The dogma of mechanism may continue to spread in other sciences and gain even wider acceptance as a popular philosophical creed. But within the domain of the physical sciences, certain mechanical conceptions become suspect with a wholesale rejection of classical mechanics which becomes identified with Newtonian physics is called for. Einstein, for example, quotes the passage from Helmholtz that James had cited, in which Helmholtz goes on to say that the vocation of physics will be ended as soon as the reduction of natural phenomena to simple forces is complete. The mechanical view, most clearly formulated by Helmholtz, Einstein concedes, played an important role in its time. But he adds, it appears dull and naive to a 20th century physicist. Einstein reviews the assumptions which physicists had to make in order to construct a mechanical theory of light, gravitation, and electricity. The artificial character of all these assumptions, he says, and the necessity for introducing so many of them, all quite independent of each other, was enough to shatter the belief in the mechanical point of view. In the attempt to understand the phenomena of nature from the mechanical point of view, he continues, throughout the whole development of science up to the 20th century, it was necessary to introduce artificial substances like electric and magnetic fluids, light, corpuscles, or ether, corpuscles, or ether. According to Einstein, attempts to construct an ether in some simple way have been fruitless. But what is more important, in his opinion, such failures indicate that the fault lies in the fundamental assumption that it is possible to explain all events in nature from a mechanical point of view. Does this mean that the contemporary physicist has found another and better way of explaining nature? Is there a non-mechanical way of explaining the phenomena which fits the mathematical laws of experimental physics? Or does discarding mechanics mean relinquishing all efforts to explain nature? Eddington suggests an answer. One of the greatest changes in physics between the 19th century and the present day, he writes, has been the change in our ideal of scientific explanation. It was the boast of the Victorian scientist that he would not claim to understand a thing until he could make a model of it. And by a model, he meant something constructed of levers, geared wheels, squirts, and other appliances familiar to the engineer. Nature, in building the universe, was supposed to be independent on just the same kind of resources as any human mechanic. The man who could make gravitation out of cogwheels, would have been a hero in the Victorian age. Today, however, Eddington continues, we do not encourage the engineer to build the world for us out of his material, but we turn to the mathematician to build it out of his material. We may turn to the mathematician's construction of the world in his terms, but in the tradition of Western thought, mathematically formulated laws of nature are not, with the single exception perhaps of the Pythagoreans, regarded as explanations of why things behave as they do, or how they work. The change from the 19th to the 20th century with respect to our ideal of scientific explanation cannot then be the substitution of the mathematical for the mechanical account of why and how. The shift from mechanics to mathematics is rather a shift from explanation as the scientific ideal to the statement of laws which, while having maximum generality, remain purely descriptive. What Eddington means by building the world out of the material of mathematics seems to be the same as what Galileo means 4 centuries earlier when he says that the book of nature is written in mathematical language. The materials are such symbols as triangles, circles, and other geometrical figures. Without the help of these, Galileo writes to Kepler, nature is impossible to comprehend. But does the mathematical comprehension of nature mean a causal explanation of it? More explicitly than Eddington, Galileo insists that explanation, at least in the sense of stating the causes, is not the business of the mathematical physicist. In a passage which cannot be read too often or examined too closely, he names 3 opinions which the philosophers have expressed about the cause of the acceleration of natural motion. Some, he says, explain it by attraction to the center, others to repulsion between the very small parts of the body, while still others attribute it to a certain stress in the surrounding medium, which closes in behind the falling body and drives it from one of its positions to another. Now, all of these fantasies, he continues, and others too, ought to be examined, but it is not really worthwhile. They ought to be examined by philosophers, perhaps, but debating them is not worthwhile in those sciences where mathematical demonstrations are applied to natural phenomena. Perfectly defining the program of mathematical physics, Galileo sets himself a limited task. Merely to investigate and to demonstrate some of the properties of accelerated motion, whatever the cause of this acceleration may be. It should be noted that of the 3 opinions about causes which Galileo mentions, the first, which anticipates Newtonian attraction, is no less summarily dismissed than the third, which summarizes the Aristotelian theory. What I call attraction, Newton later writes, may be performed by impulse or by some other means unknown to me. I use that word here to signify only in general any force by which bodies tend towards one another, whatsoever be the cause. It is well known, he asserts, in the same passage of the Optics, that bodies act one upon another by the attractions of gravity, magnetism, and electricity. But he goes on, how these attractions may be performed, I do not here consider. Newton's attitude toward causes and explanation would seem to be identical with Galileo's. Galileo calls opinions about causes fantasies and dismisses them. Newton calls them hypotheses and seems to banish them as resolutely. Hypotheses are not to be regarded in experimental philosophy, he declares in one place, and in another, having just referred to predecessors who feigned hypotheses for explaining all things mechanically, he says that, on the contrary, the main business of natural philosophy is to argue from phenomena without feigning hypotheses. The task of the physicist, who is both experimental and mathematical in his method, Newton plainly states, is to derive 2 or 3 general principles of motion from phenomena, and afterwards to tell us how the properties and actions of all corporeal things follow from those manifest principles. This would be a very great step in philosophy, though the causes of those principles were not yet discovered. And therefore, he says of his own work, I scruple not to propose the principles of motion above mentioned, they being of very general extent, and leave their causes to be found out. The 2 or 3 principles of motion mentioned in the passage from the Optics are the foundation of Newton's other great work, the mathematical principles of natural philosophy. Its title indicates the clearly conceived intention of its author to limit himself to the program of mathematical physics on which both he and Galileo seem to agree. He will not try to define the species of or physical qualities of forces. He will only investigate the quantities and mathematical proportions of them. In the general scholium with which the mathematical principles concludes, Newton disavows once more any knowledge of the causes of gravity. To us, it is enough, he says, that gravity does really exist and acts according to the laws which have been explained, and abundantly serves to account for all the motions of the celestial bodies and of our sea. Admitting that he has not been able to discover the causes of gravity from phenomena, Newton flatly reiterates his policy, I frame no hypotheses. In view of this policy, how does the name of Newton come to be associated with the triumph of the mechanical point of view in physics? Why do contemporary scientists like Einstein identify Newtonian physics with classical mechanics? If a mathematical physicist like Newton or Galileo refrains from guessing at or asserting causes, how can he be charged with having indulged in the impurity of a mechanical explanation of the phenomena, I frame no hypotheses. In view of this policy, how does the name of Newton come to be associated with the triumph of the mechanical point of view in physics? Why do contemporary scientists like Einstein identify Newtonian physics with classical mechanics? If a mathematical physicist, like Newton or Galileo, refrains from guessing at or asserting causes, how can he be charged with having indulged in the impurity of mechanical explanation of the phenomena and with having foisted a mechanical conception of the universe upon mankind? The answer to these questions, so far as Newton is concerned, may be partly found in his own writings. He did not, it seems, entirely disavow an inquiry into the cause of attractive force, as in itself either misguided or irrelevant to science. We must learn from the phenomena of nature, he tells us, what bodies attract one another, and what are the laws and properties of the attraction, before we inquire the cause by which the attraction is performed. This statement postpones, but does not exclude, an inquiry into causes. In another statement, Newton even gives us a reason for the postponement in mathematics. He says, we are to investigate the quantities of force with their proportions consequent upon any conditions supposed. Then, when we enter upon physics, we compare those proportions with the phenomena of nature, that we may know the several kinds of attractive bodies. And this preparation being made, we argue more safely concerning the physical species, causes, and proportions of the forces. These remarks of Newton do not give the whole answer. For the other, and perhaps more important part of it, we must go to the actual development of physical science in the 17th century. The steps in this development, largely discoveries and formulations made by Galileo, Huygens, and Newton, lead to crises from which the scientists could not extricate themselves without discussing causes, the causes of gravity and of the propagation of light. We may thus be able to understand why Newton could not abandon the search for causes, and why, in the queries he appended to the optics, he proposes a mechanical hypothesis in order to explain how the attractive force of gravity exerts itself across great distances, and also defends his mechanical theory of light against the equally mechanical but different hypothesis of Huygens. It might well be regarded that, though Galileo's pure position initiated modern mathematical physics, it was the persistence of impurity in the worrying about causes, or even the inescapability of such concern, which caused great scientific advances to be made the concern about causes to be made, period. The concerns about causes seem to provide, time and time again, the pivot for new discoveries. The causes are not found, but new hypotheses are made, and these, when employed, lead to wider, more general results in the form of more inclusive, unifying laws. We see this happen not only to the study of gravitation and light, but also in the investigation of heat and electricity. The concern of Faraday, for example, to explain electrical attraction and repulsion in terms of the action of contiguous particles, and to establish the existence of physical lines of force, leads to Maxwell's theory of the electromagnetic field and his field equations, combined with Faraday's speculations concerning the relation between electrical and gravitational attraction, lead to the attempt on the part of contemporary physics to construct a unified field theory covering all physical phenomena. Physics may return in the 20th century to the purely mathematical character it had at the beginning of its modern development, but as may be seen in any introduction to recent physics written for the layman, it is necessary to mark the influence of mechanical conceptions upon scientific theory, scientific discovery, and thoughts, in order to understand the difference between the unifying mathematical laws of the 17th and 20th centuries. As we retrace the steps, we see how fertile is the interplay between mathematical insights and mechanical hypotheses. As Fourier tells the story of rational mechanics, the discoveries of Archimedes begin the science. This great geometer, he says, explained the mathematical principles of the equilibrium of solids and fluids. About 18 centuries elapsed before Galileo, the originator of dynamical theories, discovered the laws of motion of heavenly bodies. Statics and dynamics are related as the two parts of mechanics when that is conceived narrowly as the science which treats of the local motions of inert or inanimate bodies. The rest or equilibrium of bodies, which is the subject of statics, can be thought of as a limiting case of their motions to which the principles of dynamics apply. In the 18 centuries between Archimedes and Galileo, little progress is made in mechanics. So far as statics is concerned, Archimedes, according to Galileo, by the rigor of his demonstration, established the science in all its essentials. Since upon a single proposition in his book on equilibrium depends not only the law of the lever, but also those of most other mechanical devices. Pascal may later enlarge statics by showing in his treatise on the equilibrium of liquids that a vessel full of water is a new principle of mechanics, a new machine which will multiply force in any degree we choose. In other works, Pascal extends these conceptions further, as in his treatment on the pressure of air. But at the time of Galileo, it could be said that although Archimedes had offered an exemplary model of mathematical physics, no progress was made until the work of Galileo's immediate predecessors. Not without assistance from certain predecessors like Stevin, Galileo founds the science of dynamics. It may be wondered why, with the start made by Archimedes, no earlier application of his principles and method had been made. The answer may be found in the physics of Aristotle. His theory of the four elements carried with it a doctrine of natural motions to different natural places, drawn from the observation of fire rising, stones dropping, air bubbling up through water. Such a doctrine would prevent the search for laws of motion applicable to all bodies, and the general character of Aristotle's physics, treating qualities as well as quantities, seems to have discouraged the application of mathematics, even to the study of local motions. The mathematical expression of the laws of motion is Galileo's objective. His interest in the new astronomy, which affirmed the motion of the earth, led him, he told Hobbes, to the careful study of movements of the earth. His aim is simply to describe with precision the motions to be found in a child's play, stones dropped and stones thrown. The one the natural motion of free fall, the other the violent motion of a projectile. It is clear to observation that the motion of a freely falling body is accelerated. But though as a mathematical physicist Galileo refrains from asking why this is so, he is not satisfied to know simply that it is so. He wants to know the properties of such acceleration. What is the relation of the rate of increase in velocity to the durations and distances of the fall? How much increase in velocity is required and how fast? What is the body's velocity at any given point in the fall? Similarly, when Galileo turns to projectiles, he wants to know not merely that their trajectory is consistently curvilinear, but precisely what curve the path of the projectile describes. Galileo succeeds in answering all these questions without being perturbed by any of the philosophical perplexities connected with space and time, nor does he allow questions about the forces involved in these motions to distract him from his purpose to demonstrate everything by mathematical methods. With mathematical demonstration, he combines observations and experiment, and uses the latter to determine which mathematical conclusions can be applied to nature, which principles can be empirically verified as well as mathematically deduced. One of Galileo's principles, however, seems to outrun ordinary experience and to defy experimental verification. In the interpretation of his experiments on inclined planes, Galileo expresses an insight which Newton later formulates as the first law of motion, sometimes called the law of inertia. It declares that every body continues in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed upon it. Though Newton describes his method as one of making experiments and observations and in drawing general conclusions from them by induction, the law of inertia seems to be an exception, for it is difficult to say, as Hume does, that we find by experience that a body at rest or in motion continues forever in its present state. That is, unless it is acted on by some new force. The condition introduced by unless raises Poincaré's question. Have there ever been experiments on bodies acted on by no forces? If not, and if they are impossible, then James may be right in saying that the elementary laws of mechanics are never matters of experience at all, but have to be disengaged from under experience by a process of elimination. That is, by ignoring conditions which are always present. Because the idealized experiment which is called for can never be performed, the law of inertia, according to Einstein, can be derived only by speculative thinking, consistent with observation. In any case, the first law of motion initiates a new departure in physics. So far as local motion is concerned, Aristotle and his followers look for the cause which keeps a moving body in motion or a stationary body at rest. According to Galileo and Newton, uniform motion continues naturally without cause. Only a change in the velocity or direction of the motion requires a cause, such as a force impressed upon it. How radical this innovation is may be judged from its consequences in celestial mechanics, which in turn lead to a completely unified dynamics for both celestial and terrestrial motions. These advances are the work of Newton's mathematical genius, but the ground for them had been laid by the investigations of Galileo. Galileo had resolved the curvilinear motion of a projectile into the imparted rectilinear motion and the deflecting pull of gravity. This composition of forces, sometimes called the parallelogram law, explains why the path of the projectile is a parabola. The path of the planets in their orbits, Kepler had previously shown, is another conical curve, an ellipse. But Kepler, lacking the first law of motion, could theorize physically about the cause of the planetary orbits, but only by looking for a force projected outward from the sun, which would sweep around to keep the planets moving in their paths. On the other hand, a follower of Galileo, as Whitehead points out, would seek for normal forces to deflect the direction of motion along the curved orbit. He would look for a force pulling the planet off its own rectilinear course inward toward the sun. That is precisely what Newton did. When the problem, which others had been able to formulate, was put to Newton, he simply went to his study for the solution. He had solved that problem some years before. He had found the law of the force which, attracting the planets to the sun, would produce their elliptical paths, and the other proportionalities stated in Kepler's purely descriptive laws. With that single discovery, Galileo's terrestrial dynamics became a celestial one too, and the traditional separation of the heavens from the earth is overcome. Newton goes even further. He guesses, and then shows by arithmetic, that the force deflecting the planets around the sun and the moon around the earth is the same force which makes apples fall and stones heavy in the hand. He generalizes this insight in his famous inverse square law. Every particle of matter attracts every other particle of matter with a force proportional to the mass of each and to the inverse square of the distance between them. Accordingly, the world can be pictured as one in which material particles each have position in absolute space and a determinate velocity. The velocity of each particle causes the change of its position, and changes in velocity are caused by forces, the amounts of which are determined by positions. From his laws of motion and this simple law of force, Newton is able, by mathematical deduction, to account for the perturbations of the moon, the oblateness of the earth, the precession of the equinoxes, the solar and lunar tides, and the paths of the comets. But in Newton's law of force, as simple as it appears to be at first, but is Newton's law of force as simple as it appears to be at first? Its mathematical meaning is plain enough, and its application to measured phenomena reveals its descriptive scope. When we ask, however, about its physical significance, we raise difficult questions concerning the nature of this attractive force and how it operates. To call it the force of gravity, and to point out that this is a familiar force which everyone experiences in his own person, hardly answers the question.